By definition, moving charged particles constitute an electric current. You must have seen that during lightning, charges flow from the clouds to the earth. This flow of charges is not steady but momentary. Or you must have observed that charges accumulate on the metal body of a chair. When you touch this with bare feet, you experience a mild shock. This is because these charges get short-circuited through your body and reach the earth. These are examples of a very short duration or momentary electric current. In most of the devices that we use, there is a steady flow of charge. For example, in the working of an electric bulb, a steady current passes through the circuit of the bulb to make it glow. Now, to better understand the concept of electric current, let us conduct a simple virtual activity. In a closed space, a large number of positive and negative particles move around randomly. Divide the space into two parts using a vertical plane surface through which the charges cannot cross over. Cut a rectangular shaped window in the vertical surface. Now, the charged particles can move from left side of the partition space to the right side and vice versa through the window opening in the vertical plane surface. Let us now form a sign convention for the motion of the charged particles. The left to right motion of any charged particle is taken as the forward direction of motion, which is taken as positive. The right to left motion of any charged particle is taken as the backward direction of motion, which is taken as negative. In time t, which is equal to 10 seconds, let us assume that the number of positive charged particles crossing over from left to right is equal to A, which is equal to plus 50. The number of positive charged particles crossing over from right to left is equal to B, which is equal to minus 10. The net positive charge movement is equal to A plus B is equal to C, which is equal to plus 40. The number of negative charged particles crossing over from left to right is equal to D, which is equal to plus 30. The number of negative charged particles crossing over from right to left is equal to E, which is equal to minus 20. The net negative charge movement is equal to D plus E is equal to F, which is equal to plus 10. The net charge movement Q is equal to C minus F, which is equal to 30. A steady electric current I is denoted by Q by T. By substituting the values of Q and T, we get the value of I as free units. A steady current is positive when it moves under forward direction, that is, from left to right, and negative when it moves in the backward direction, that is, from right to left. Instantaneous current at any time t is expressed as IT is equal to limit t tending to 0 delta Q by delta t, where IT is the current at time t. Delta Q is the net charge flowing across section during the time interval delta t, that is, between time t and t plus delta t. The SI unit of current is ampere and is represented by A. From the previous activity, we have observed the random motion of the charged particles within an enclosed space. During the random motion, the charged particles not only collide with each other, but also with the wall of the enclosed space. After collision, they get deflected and move again randomly with the same velocity with which they collide. When an electric field is applied to the enclosed space, the random motion of the charged particles is changed to unidirectional flow that constitutes an electric current. Now the question arises, what are these moving charged particles that constitute an electric current? In individual atoms and molecules, the negatively charged electrons and positively charged nuclei are bound to each other and therefore are not free to move independently. Bulk matter is made up of a very large number of atoms and molecules, which are so closely packed that the electrons are no longer attached to individual nuclei. There are some materials whose electrons are totally bound to their nuclei and can't be separated even on applying an electric field. These materials are called non-conductors or insulators. In metals, some electrons are practically free to move within the bulk material. These electrons are called free electrons. When an electric field is applied across metallic objects, an electric current develops in them due to the unidirectional flow of these free electrons. Therefore, metals are called conductors. In the future modules, we will emphasize on solid metal conductors, where the metal is constituted by the movement of negatively charged free electrons in the background of fixed positive ions. Consider a metal object when no electric field is present. Electrons in the object will be moving in randomly and colliding with the fixed ions. An electron, after colliding with an ion, gets deflected with the same velocity with which it collides. The direction of velocity of the electron after collision is completely random. There is no preferential direction for the velocities of the electrons. On average, the number of electrons traveling in any particular direction will be equal to the number of electrons traveling in the opposite direction. Therefore, there is no net electric current. Let's apply an electric field to the metal and see what happens to the motion of these electrons. To observe the motion of electrons very clearly, let us use a conductor in the shape of a cylinder of radius r. We take two thin circular discs made of dielectric material of the same radius r as that of the cylinder. There are few number of positive charges distributed across one of the discs and few number of negative charges distributed across the other disc. These two discs are attached to the two flat surfaces of the cylinder, creating an electric field which is directed from the positively charged disc to the negatively charged disc. The electrons are accelerated and move towards the positive charge. On reaching the positive charge, they neutralize the charges on the disk. The unidirectional motion of these electrons constitutes an electric current. This electric current exists only for a very short time, that is, till the charges are neutralized. We can attach the two ends of a battery or a cell to the two disks to maintain a steady electric field and thereby maintain a steady current.